record. Okay, and now I get back to where I was. Okay. All right, you cannot minimize Zoom. Wow. Let's do that. Okay, let's see. If u is sine of 6x, then sine squared of 6x is u squared. And I get the 1/6 from this 6 right there.
Mr. Cohen, are you sharing the screen? I just see it's just like a blank page.
Oh, I must have turned that off accidentally. Wow.
I thought it was
do that. Thanks for telling me. Go to Zoom again and share the screen.
There we go.
Now you can see it. And now I need to bring up that whiteboard again.
Did you close it?
Might have accidentally. Hold on. It's going to show.
No,
I think I still have it. Yeah. Okay. I think we're good back. I think we're recording it and we're also.
And it will save all this work too. Like if you just hit that back arrow, it saves this whiteboard and all the work you've done on it.
Okay.
Anyway. Okay. So we have that one.
So, yeah. So the question is, oops, I keep doing that. Oh, God, really got to be careful here.
We can take that 1/6 out. So that could just
okay, so let's do that. But the first thing I want to do is make sure that that is the same as this. So u is definitely sine of 6x. So u squared would be sine squared of 6x. So that gives me the u squared in the denominator. And if u is that, then du is 6 cosine 6x dx. Dx is du divided by 6 cosine of 6x. And the cosine, that cosine of 6x cancels with that cosine of 6x, and we're left with a 1/6, and which we can now take out as a 3. Okay. So the integral of that is minus cotangent.
Yes. Yeah.
Divided by 6. Right?
Right.
Okay.
At least that's what
and this was a +3. And now we have the integral of 1 over u squared. So that is going to be let's see, that's u to the -2. So we're going to make it u to the -1 over -1, which changes this -3 to minus. And that's that.
Sine squared then.
Okay, here we got it. We got it. Just realized. That's 1 over u. 1 over u is 1 over sine 6x, which is cosecant.
Okay. Which is...
So we were able to use u substitution to prove that, in other words, we didn't have to experiment with 100 different identities to try to find the one that you can integrate. we could do this with the U substitution. And the reason I saw it is because if U is sine of 6x, then the derivative of that is cosine. And you always want it to be a multiplier.
Right.
And it is a multiplier. So it definitely lends itself to U substitution.
Okay.
And that is the correct answer?
Yes, that is the correct answer.
And then
we could factor out the 3.
Yeah, you could factor out a 3 or a -3, whatever you want.
Because that's that.
And yeah, one of the key things to recognize here is that it doesn't matter whether you factor out a -3 or a 3, it does not change that. C is not affected.
Right, because it's all real numbers, essentially.
It could be any number. Okay. So C divided by 3 is the same as C.
Right.
That's the essence that you want to keep in mind.
Yeah, and that part is not difficult. It's actually, again, this is not so much calculus as it is heavy on trig.
So, absolutely. This was really more of a trig problem than it was calculus.
Exactly.
Although you do need to know your antiderivatives.
Exactly. No,
and U substitution. We had to use it. So it's a little bit of both calculus and trig. But you're going to find that as you go forward in calculus, the trig is more and more involved, which I find very interesting because, as I said last time, trig started out to be an analysis of triangles. That's what it was originally developed for. Mm-hmm. And it turns out to be a critical tool in integration and differentiation. Because sometimes you end up with polynomials that cannot be integrated unless you change them into trig functions. And then you can integrate the trig functions and then you change them back into the polynomials. And so that is one method of integration. You haven't learned it yet, but it's called integration by trig substitution. And the concept is absolutely that you start with a polynomial that you have no idea how to integrate. You convert that polynomial into a trig substitution, and then you're able to integrate it because it's now a trig function and you know the antiderivatives of trig functions. So you integrate it, and then because you know what the substitution was, you can turn it back into a polynomial. And that's one of the tougher techniques of integration, is integration by trig substitution, because you kind of have to draw triangles and label the sides, and it's quite a difficult concept. If you want to study anything, study your trig identity.
Yeah, I can definitely tell it's coming back with a vengeance.
Yeah, but also learn to recognize this pattern recognition.
Yes. No,
in other words, that is huge. I don't know why I didn't recognize it the first time I saw it. I fooled around with all the trig identities, and eventually when you told me the answer, I was able to prove that that was equal to minus cosecant cotangent. But how one would know that is very, very difficult. And the easier way to do it is to just recognize that you have the derivative of u in your numerator.
Okay.
That's pattern recognition. That's okay. 3/4 of your U substitution is going to be pattern recognition. More than that, probably 90%. The other 10% will be change of variables. But most of the time, you're going to be dealing with pattern recognition where you have the derivative of U as a multiplier, just like this. If U is sine of 6x, the derivative of U is cosine of 6x, and it is a multiplier.
Okay, no, that makes sense. And just real quickly, Mr. Cohen, at a high level, we multiply by 1 essentially, so that we'll get in this case, the trig identity would be sine squared. Now we have a monomial in the denominator.
That's the key. So that's why you do this step, right?
Okay.
Is to turn this binomial into a monomial. Because once we multiply by this number one, the bottom becomes sine squared. Okay. And that's a monomial term. So then we can separate it into two fractions. Which we cannot do. So it's a bit like change of variable. In fact, I'm wondering if we couldn't have used change of variable here, where we let u equal 1 minus cosine 6x. Might actually work better. I don't know. I'm not going to waste your time doing it.
I'll try it again.
Change of variable is frequently used when you have a binomial denominator that you're wanting to turn into a monomial. Kind of like if you have x over x plus 1. I can't do the integral of that. But if I let u equal, if I let u equal x plus 1, now the numerator becomes u minus 1 over u. And I have a monomial term in the denominator, which means I can separate it into two fractions and do it.
Right, okay. And then the other key here is recognizing that the derivative was in the numerator for the second egg. That's
huge. That is really huge. Let's see, how do I clear everything here?
Click on the eraser.
There you go.
And then there you go.
Yeah.
I need to right click or something. Yeah, something like that.
Yeah, if I had something like the following. Notice that if u is going to be sine x, and the derivative of u is cosine x. So that's the pattern I'm looking for. And it doesn't really matter whether the sine x is in the numerator or the denominator. The fact is that I need the multiplier to be the derivative of the inside. Okay. And the inside is sine x. In other words, I'm going to let u equal sine x, which means du would be cosine x, dx. And now dx is going to be du over cosine x. And you can see where the cosine x disappears.
Right.
And you end up with u to the 6th du, which is very easily done.
Right. Okay.
So always look for that as your first step, where whatever you would let u equal, if it's being multiplied by the derivative of u, you're in business using u substitution.
Okay. Yeah, because that's going to be a lot easier to resort to than just trying to figure out the trig identity.
Yeah, we could be working all day trying to turn that into something that we knew the integral of or the antiderivative of. And I didn't see it the first time I looked at it. I just started changing it with all the identities I knew, and I couldn't quite get it. But if I'd have recognized it as u substitution, we'd have gotten it right away.
All right, Mr. Cohen. I'll let you go on that note. I'll set up an appointment tomorrow though, because I still had 2 more questions on the homework, but this one was the most boogie one. So
yeah, well, thanks for teaching me whiteboard, because
I think you'll like this. And
for calculus for sure. I don't really need it for anything else because only calculus requires is more than a page long. Yeah, right. I don't have to erase and stuff.
At least for me, it'll be nice because I have to see this, like I have to work through this and then see the whole process for it to click.
Oh, I don't blame you. That's the way most people work. They need to see it all.
Right. So this is super helpful for me, if for nothing else.
Yeah.
All right, Mr. Cohen. Appreciate your time.
Okay, Connor.
Have a good one.
Talk to you later. Bye-bye.